Okay, so this question is actually a lot like the ones we solved in class. It's kind of one of those riverboat crossing questions where you need to take into account both the velocity caused by the boat's motor as well as the river current in order to understand how the boat is moving with respect to the shore. So the question set up, they give us the width of the river is 260 meters. The direction of the current is this way. The boat is aimed at a 45-degree angle with respect to the shore, but because the river current is also moving, the boat is actually going to take a path that's sort of like that, right? Because when you combine the motion of the current this way and the boat trying to go that way, the resultant motion actually ends up being in this direction. They also give us the speed of the boat in still water. And the question that they give us is, well, what is the current, right, in order for the boat to land at this point, right? They give us the displacement upstream that the boat travels as well. So before we can answer that, we need to think in terms of vector addition. So the velocity of the boat in still water, I'll call that VB, and the velocity of the current, I guess this is really a speed, right? Because that's the magnitude of the boat's velocity in still water. The speed of the current, well, we can call that, let's say, VR. Right, so if we were to combine these two vectors to find the net velocity of the boat, well, it would look something like this. Right, V boat is that way, in this direction, right? This is its magnitude. V river is that way. Maybe I'll write this below here. So the total velocity of the boat would look something like this. We'll call that V net. Right, that's the resultant vector. So now in order to actually find this resultant vector, well, we need to break the velocity of the boat up into its two components, and then we need to use those components to combine with the velocity of the river. So here's what I mean. So let's think about just the velocity of the boat. Right, so here's our boat velocity. Let's break this up into a vertical and a horizontal component. And just for the sake of simplicity, I'm going to go ahead and define some directions. So I'm going to call this way the x direction and up the y direction. Right, so if we break the velocity of the boat up into components, this component would be VBX component, and this would be VBY component. That's theta right there. So we can write VBX as VB cosine theta and VBY as VB sine theta. Right, those are those two components. Now, the net velocity of the boat has to include the velocity of the river, which is in the negative x direction. Right, so if we wanted to write this in vector form, right, we could do that. That wouldn't be too tricky. It would just be like this. We could say V boat vector is VB cos theta, VB sine theta. Something like that. Am I still on the screen? Yes, I am. Okay. So that's V boat. V river, right, that would just be negative VR. Right, VR represents the magnitude of the river's speed. Right, negative I put because it's flowing in the negative direction. And this river has no speed in the y direction. So if we're going to combine these components, well, we end up with the net velocity of the boat looking something like this. VB cosine theta minus VR, right? I'm adding x components. And then the y component is just VB sine theta plus 0. So that's the total velocity of the boat, right? And these would be the components of this V net vector over here. Now, what we can actually do with this is we now have velocity in the x direction and the y direction. We can write equations to describe the boat's motion in the x direction and the y direction. So what that would look like, in the x direction, we've got Vx, this is equal to Vb cosine theta minus Vr. Well, that should be equal to its horizontal displacement, right? That's the x displacement, over the time for which it travels. Similarly, we could write Vy, which is Vb sine theta, right? That is equal to its displacement in the vertical direction per time. Right? We've actually done all of the physics now. In order to solve the question, it's just a matter of algebra. Because we know the speed of the boat, right? That's the speed of the boat in still water. We know the angle. We know the horizontal displacement. Right? We also know the vertical displacement. We've got two equations, and we've actually got two unknowns. Right? Our unknowns are delta t and Vr. So we should be able to solve for the unknown we want. That's Vr. So in order to do that, I'm going to plug these two equations into each other. And I might go ahead and get rid of this equals sign really quick, just to sort of make those look a little more clean. So in order to plug those equations into each other, what I'm going to do is I'm going to solve this for delta y, or for delta t. So delta t is delta y over Vb sine theta. And now I can plug that into here. Right, so Vb cosine theta minus Vr is equal to delta x over delta y, and then this is in the denominator over here, so it ends up in the numerator actually. Right, I just took this and I plugged it in for delta t here. And now our goal is to solve for Vr, so I'm going to subtract this over here and move Vr over there. So it's Vb cosine theta minus delta x Vb sine theta over delta y equals Vr. There we go. Right. Plugging in numbers ought to give us our answer. I don't think I'm going to take the time to do that because you can just look at the solution. But there we go.